The purpose of this video is to demonstrate advanced flow control using an Equilibar back pressure regulator and an Endress Hauser flow meter in a closed loop control using a LabVIEW program. Our Endress Hauser flow meter is a ProMass 63 from the 1990s. It's a DIN 2 unit and its span is to 1,000 grams per minute.
Before getting into the physical setup we are working with, here is a schematic from our Getting Started with Flow Control brochure. We have water coming in, shown on the left, through the flow meter, and then through our Equilibar flow control valve, and emptying out to atmosphere. The LabVIEW I/O cards are getting a signal in from the flow meter, which is being run through a PID loop, and then sending a signal out to the QPV. That's directly piloting the flow control valve. The laptop in this schematic is used to control the PID parameters and the set point for the system.
Water is coming into the system at 3 bar from a pressurized tank. It is then going through the Endress Hauser flow meter and into an Equilibar FDO4 back pressure regulator, which is a 1/2 inch unit. The back pressure regulator is dome loaded, so it is getting a set point pressure from this Equilibar QPV high resolution electronic pressure regulator. The QPV is being controlled by a PID loop through LabVIEW. Looking further into our LabVIEW setup here, this is the chassis we are using to connect these 4 data acquisition devices to our LabVIEW system. For this particular program, we're only using the NI9203 and NI9265 cards. The 9203 is a 4 to 20 milliamp analog input module that's acquiring data from both the Endress Hauser flow meter and the QPV monitor. And this 9265 card is a 4 to 20 milliamp analog output card that's delivering the drive signal to the QPV. We also have over here a power supply, and you can see how we interface these with our devices on the outside of our box with banana plug connections. Here is the 9203 module on this left-hand side. This is the signal out of the Endress Hauser and into the card, and this is the signal out of the QPV monitor. This is the 9265 card, and what you see here is the analog input to the QPV itself. And over here is the power supply connections.
Here's a look at the block diagram we are using for this setup. Starting at the very left-hand side, you can see the DAQ Assistant module labeled milliamp in-9203. And by double-clicking on that, we can see the settings we have for that DAQ Assistant. There are 2 variables being read by this 9203 DAQ card. The first one we're looking at right now is the Endress Hauser flow meter. It is being sampled continuously, and it's coming in as a 4 to 20 milliamp signal. It needs to be scaled, so in the bottom right-hand corner, you can see the scale that's being used. By clicking on that wrench button right next to the scale in the bottom right-hand corner, that brings up this next dialog box. It's showing us that the scale being used is mapping the ranges of 4 to 20 milliamps to the full range of the flow meter, which is 0 to 1,000 grams per minute. Closing out of that and switching over to the QPV monitor channel, you can see that it's also coming in as a 4 to 20 milliamp signal. It's also being sampled continuously, but the scale in this case is different. In this case, instead of mapping the ranges of the full scale, I used Excel's linest function to find the y-intercept and the slope of the line of best fit when mapping this 4 to 20 milliamps to the scale of the QPV, which is 0 to 150 psig. Closing out of the DAQ Assistant settings, we are back to the block diagram. You can see that the DAQ Assistant for the 9203 module that we were just looking at is splitting into 2 signals. The first one is the Endress Hauser flow meter, and the second is the QPV monitor. The Endress Hauser signal is being used as the process variable for the PID loop, and the set point control is being used as a set point for the PID loop. There are also PID gains and an output range defined in the front panel. And this PID is outputting in grams per minute, so that signal is being converted linearly back to a 4 to 20 milliamp signal, which is then being delivered to the milliamp out 9265 DAQ Assistant, which is directly communicating to the QPV via that 9265 card. If we take a closer look at this next milliamp out -9265 DAQ Assistant, you can see that there's only one channel configured in that card, and that's outputting 4 to 20 milliamps directly to the QPV. So there's no scale in this case, and that's why we had to convert the signal from grams per minute to milliamps on the block diagram. The generation mode in this case is also set to 1 sample on demand. Going back to the block diagram, you can see that Endress Hauser signal is also being averaged over 20 samples and then delivered both to a numeric indicator and the first input of the waveform chart. The second output from the 9203 module, the QPV monitor, is also being averaged over 20 samples and then being delivered as the third input for the waveform chart. This second input for the waveform chart is the set point, and that's the same one being used by the PID loop. Now we are looking at the front panel of the LabVIEW code we are running. The graph here is showing the set point in red, the flow through the meter in white. Both of those are using the scale on the left, and the green line is the QPV monitor, which correlates to the pressure on the dome of the Equilibar FDO4, and that scale is on the right-hand axis. The flow meter has a capped range of 0 to 1,000 grams per minute, so I started with a set point of 10 grams per minute. You can see that the set point is stable either by looking at the graph, which is now at 50 grams per minute, or this box in the left-hand corner. And now I'll make another change to 200 grams per minute. One really important part of the flow control system design is the high-resolution QPV electronic pressure regulator. It makes small changes to the set point of the dome on the Equilibar FDO4 that result in large flow changes, as you can see in this chart. And by jumping up to the full 1,000 grams per minute on this flow meter, we achieve a 100-to-1 turn-down ratio for our system. We can also do larger set point changes. We've been stepping up pretty gradually, but I can make a really large change from 1,000 grams per minute all the way down to 100, and you can see how fast the QPV and, in turn, the FDO4 respond to this set point change.